Okay, we are recording now. So this session isn't going to be so much a part 2 as it's going to be a redo. We're going to basically cover everything that was covered in part 1, as well as finish the whole journey from idea to the completion of this project. Now, an alternate title that I had always thought of for this type of presentation was, standing on the shoulders of giants. When you do a project like this, you're really building on the work of a lot of other people. First off, the Linux kernel. Last time I checked, the Linux kernel is 18 million lines of code. Those are some pretty wide shoulders to stand on. So the Beaglebone Black board, running Debian Linux, that was a huge step up in getting this project done. Also, resources. Okay, I want to thank everyone who devoted some of the time to answering questions and helping me to get this project done. So just to start, we do have a GitHub. We have a GitHub repository for this whole project. You can find it under CADSoft Computer, and there will be BBB, Wi-Fi radio. Everything is here. The Eagle files. I even kept the data sheets up here, the device tree overlay, the software that I used, all of the code. You'll find all of the links to various tutorials and things that I used to set this up. So, everything is here documented. If you guys ever have any questions, my email is here as well. So feel free, okay? This is all available for you guys to use and take advantage of. Another huge resource is the Beagleboard group, okay, the forums. This is the official community page. Invaluable, okay? Definitely, if you're going to do any projects with the Beagleboard, the Beaglebone Black, any of those derivatives, go ahead and set up an account here. Ask away. Very responsive. Big shout out to Robert Nelson and a few of the other guys that helped me out. Another person very, very instrumental, Dr. Derek Malloy. He's a professor. His site, Exploring Beaglebone Black, and his personal site, incredible resources. This section helped me a lot in setting up the device tree overlay. So definitely, big resource for the Beaglebone Black. Adafruit has a lot of good resources for the Beaglebone Black. Element 14, which again was also invaluable. We'll talk about this one later. Go ahead and minimize it and put this over here. Okay, so definitely there is a wealth of resources available for finding out about the Beaglebone Black. Not everything is in one place. There were certain things that gave me a very hard time. But eventually, with the help of the community and reading some data sheets and figuring some stuff out, I was able to get a completed project, and we'll see that later on. So let's go ahead, and the first thing I wanted to cover with you guys is the hardware. So here we have Eagle open. Sure, nothing. If at any point you guys have questions, please feel free to submit them through the chat window or through the Q&A. If I can respond to them at that moment, I will. If not, I'll answer at the end. But nobody's questions will stay unanswered. And if I don't know the answer off the top of my head, then I'll research it and put the answer on the Element 14 page. Okay? So I'm going to go into the hardware design. So first off, this design that I made is based off of one that Element 14 member Shabazz came up with. Okay, so Shabazz, if you're seeing this or hearing it, I owe you, man. You really did a lot of work on which I basically based my design off of. So these are some notes that he prepared, as well as using a DAC. I ended up using the same DAC that he did. I can't access it because this thing is in my way, so bear with me 1 second, guys. Okay, which is here. He basically put up a series of blog posts using the PCM 5102 audio DAC, which is exactly the part that I used. for my design. And even though he made the schematic available, he didn't make the layout available. His board also had a lot of other stuff that I didn't need for my purposes, so I ended up stripping a lot of the design away. So in essence, I basically redrew everything from scratch and laid out the board from scratch. So even though the original design intent is his, the rest of the board is basically mine. So if we go to the schematic, there's a couple of points I kind of want to bring up. Let me go ahead and go to the files because we're going to need a few here. So a couple of things. This audio DAC is an excellent chip, very easy to find, not super expensive, and the audio quality is actually pretty good, as you guys are going to hear in a little bit. If you look at the data sheet, which is what I want to bring up now, okay, excellent part, works super well for this purpose. The audio of the Beaglebone Black, as you guys know, if you do have the Beaglebone Black, it doesn't have an audio output built in. What it has is a couple of streams, a couple of interfaces that can be used to output audio. In my case, I'm using the HDMI audio, which is output through an I2S stream. And that's exactly what this chip takes. So if we go to the application circuits, quickly, near the end, data sheet. Getting there. Almost there. Here we are. Okay. These are some of the default circuits. Basically, the one that Shabazz set up is the same thing with one minor exception, which is what I want to detail here. Go back to the schematic. Okay. All of this is the bypassing of the supplies. This chip requires 3 different supplies. There's one for a charge pump. There's one for the analog circuitry and one for the digital circuitry. The charge pump circuitry is actually very interesting because that is what helps generate negative voltages so that the output can go negative or it can be bipolar. Now, if you look, the circuit is pretty much the same thing as on the data sheet with the exception of this little circuit over here that I'm circling. Okay, where is that coming from? So basically, if we go back to the data sheet and we go to the timing diagrams, you'll see that this chip takes both the I2S data format as well as left justified format. Okay, and for our purposes, we're just using the I2S, not the left justified, which is this timing diagram right here. Okay, and if you look at the way the data is being clocked in, it always comes in on the falling edge. Okay. However, for some reason, the I2S stream outputted by the Beaglebone Black puts it on the rising edge. Okay, so that necessitates. Whoops, got the wrong file. That necessitates adding in this NOR gate, which is being used as a simple inverter. Okay, so this right here is just being used as a very simple inverter. It can be disabled by just unpopulating resistor R7 and populating R6, and that'll make it just a follower. Okay, so that's why this is here. Now it's very important that whatever chip is used here be a high-speed logic family. The input here, the clock signal here is 25.476 megahertz, if memory serves. I could be a little off on that. I haven't touched it in a bit. So that gives you about 40 nanoseconds between pulses. So the latency latency of this chip has to be very small. The data sheet, if I remember correctly, I think it's like something like 7 or 14, something in that field. But it's very low. It's a very high-speed logic chip because otherwise the data it's not going to sync up. The inversion here isn't going to show up on time in order to be able to get the data in. So very key point, you can't just use any logic chip here. It has to be a very high-speed family. We can actually check it. Let me go back to the data sheets over here. Okay, this is an exclusive OR gate. And again, by tying one of them high, I turn it into an inverter and letting the clock come in the other way. If I were to tie the remaining available pin low, then it would just become a follower. And you can see that here in the truth table. So if let's say this is the input I'm controlling. If I set it to low, then the output just follows whatever the B input is. If I set it to high, then the output is the inverse. And that's how we deal with the fact that the stream in the Beaglebone Black isn't coming in on the same edge as the chip expects it to be. Okay, and we can see some of the characteristics here. Let me find the timing characteristic. Maximum propagation delay. Okay, so typically it's on the neighborhood of 4.4 because I'm running it at 3.3 volts here. 4.4 nanoseconds. However, it can be as high as 11 nanoseconds at room temperature. This is similar to the one that Shabazz used in his design. I didn't use the exact same one. Okay, so very, very key point. You also want to keep the traces short. You don't want to add unnecessary capacitance to the circuit. So you'll notice that in the layout, that chip is extremely close to the circuit. The circuit has a couple of other parameters that can be adjusted, and I've detailed that here on the schematic. You always want to put as much information as you can on the schematic. That's, all of your design intent and all of your design logic is here in the schematic. So you always want to make sure to document as much as possible, because 6 months from now you won't remember what you did. Okay? So if you notice here, R1 is set up. It just disables the emphasis or selects normal latency. Depending on which one is populated, you can get different parameters. But by putting these in, that's the configuration that I set up for the chip. Also over here, depending on whether R4 is populated or R5 is populated, we can specify whether we have I2S or left justified. As you can see, R4 is the only one that's populated, R5 is not. I have it set up for its value do not fit. I still left it on the PCB though, because in case I needed to fix or repair something, I would be able to play with it. Okay, now let's look over here at the power supply rails. So you can see the big goal here is to keep the rails separate. They each have their own ground plane. And all of the entire goal of doing this is to minimize noise as much as possible. We really want to keep noise out of this as much as we can. As you can see down here, before I go over here, there's lots of decoupling on the power supply. I have inductors on the outputs of these power supplies, all of that just to try to filter as much as possible any noise. And the result is well worth it, as you guys will hear in a bit. I added test points all over the place. You'll see them as these little arrows. As these little diamonds over here. Okay. If you're making your first spin of a board, I highly encourage you, any signal that you think you might need to scope later or you might need to be able to probe, just do yourself a favor and put in a test point. Just make your life as easy as possible. Put in test points, because later on it's very easy to put voltmeter probes, put oscilloscope probes, and in my case I didn't end up needing them, but I was happy and I was very relieved that they were there. Okay, we have a layout question. Okay, so I'll answer that at the end, NK. Okay, I'll make sure to answer that. Bear with me 1 second. Let's continue with the presentation. After I put in all the test points, I created this little test point table, identifying what each test point was, what signal I was clocking, what signal was connected to. And that was just going to be an easy reference for debugging. I gave Shabazz his shout out over here. It's the link to his design, the pages that we showed before. Here is the Beaglebone Black part. This is made by Element 14. I ended up adding to it, so my library is actually a little bit more than the revision A you'll find on Element 14. That's why I named mine with the revision B. Okay, and over here you can see all the signals as they connect and they go over here. And the power. The last thing I want to mention on the schematic is this over here. Okay. Very key point. In Eagle, all the connections are defined by net name. So in order to connect nets that have different names together and still preserve the separate names, you have to do some tricks. And there's a lot of ways this can be done. Some guys will create jumper libraries, and they'll basically be 0 ohm resistors. So on the schematic, they'll show up as resistances or whatever symbol they choose to use. And then on the board, the actual layout, it'll be a part made up of 2 SMD pads shorted together. So as far as Eagle is concerned, there's 2 connection points, but the reality is that they're shorted by the copper. That's one way to do it. In my case, what I chose to do is put an explanatory note here and then do the connecting of the 3 grounds on the board, which I will show you guys now when we go to the board. Okay, once again, everything is properly bypassed and filtered. I just followed mostly Shabaz's lead, but then on the data sheet you'll find the same thing. So you'll see that basically it's the recommended application circuit. Put a signal flow. So here's where the I2S data enters through here, and then here's the audio output with this connector. Now let's go over to the board. Here on the board, okay, we can see the layout. I tried to keep everything as tight as I could. Here's the main chip. Here's the inverter right here. You can see very short traces. You always want to minimize traces as much as you can. Here's one regulator, here's another, and here's another. Okay, they're all feeding from the 5-volt rail that's here. All my test points. All signals as they came out. Here's the connector with the 2 filters for stereo output. Something I want to bring to your attention here, this particular connector, I'll show you guys the data sheet. I think the data sheet will show it. This particular connector, if you guys see here on the recommended PCB layout, you'll see that it uses slots. Now, Eagle by default doesn't have slotted holes. So what you end up having to do is what I did here. Okay, I used a normal pad, a normal through-hole pad, with a shape as close to what I needed as possible. So basically this was perfect. This was the exact shape I needed. The hole is obviously circular. To get the slot, I drew the slot out on an unused layer. You can use any layer that doesn't normally have data on it. In my case, I used layer 46 milling, and I drew the slot in it. Okay, when I went to generate the Gerbers, I made sure to put the information on this layer, layer 46, as its own Gerber, and I let the board house know that I needed that milled from the board. Okay, in doing so, I got the slotted effect. For future releases of Eagle, we want to have something a little bit more native, a little bit more internal to Eagle to be able to generate that. Now, if any of you guys design capes normally or use Beaglebone capes at all, you'll probably notice that there's one key thing missing here, and that's the ESProm chip. Okay, according to the system reference manual for Beaglebone Black, every cape that you're going to sell should have an EPROM. Now, I chose not to include it here for several reasons. Number one, I'm not going to sell this board. Number two, it was going to be a lot of additional work to incorporate it, and if I'm not going to sell it, then, and this is just for a personal project, I didn't see a point in doing it. And number three, even if you don't have an EPROM, there are ways to set up the Beaglebone Black to use a board you made at default when it boots up. So for those reasons, I chose not to include the ESProm chip. If you did want to find out more about it, you can go to the Beaglebone System Reference Manual, page 94 onward, and you'll find all of the information about how that needs to be set up. So let me go ahead and very quickly just show you that. Again, I downloaded all of these. Down. Oh, 94. And here's all the information you need to know about the Beaglebone Black cape system and what pins are taken by different things, and we'll run into that later when we start talking about the device tree overlays. Okay, so that in essence is everything about the hardware that I wanted to discuss. As far as the ground plane, remember how I mentioned to you guys that the digital ground, the charge pump ground, and the analog ground all need to be tied together. And I chose not to do that in the schematic, but rather here on the board. Okay, the way I did that is, as you guys are going to see now when I rat's nest, you'll be able to see the 3 different polygons. The rat's nest, and here are the 3 different polygons, okay? So what I did was I made sure they all return back to a common point. A couple of key points about doing this type of grounding arrangement. First and foremost, the 3 planes only meet at one point, which is this area over here. They're meeting right here, okay? They don't meet anywhere else within their boundaries. Second point, it's generally recommended that that point, that central point where everything meets back at, should be near the power supply. In the case of the Beaglebone Black, or this cape, the best place I could pick was here, which is basically where the 5 volt and the ground comes into my board from. So I put it over here. Now, why do this? Why bother separating the grounds if at the end you're just going to connect them all again anyway? Well, the idea behind this is that certain signals or certain parts of the circuit are noisier than others. So, for example, the digital sections tend to be very noisy because we have fast switches, fast transitions at high frequencies. So by separating the digital ground part, let's say this is it over here, by separating the digital ground part, we keep those fast switching ground currents limited to this area. This was all tied together, and there's a possibility it could move around to the other circuits and affect their noise immunity. So by doing this, all the currents do end up returning to ground, but they stay separate all the way just up until here. And that's the goal of doing this separation. Basically keeping noisy currents circulating in a certain area without having more quiet areas be affected by those noisy sections. Again, if there's any questions about this, please feel free to send them through. So hardware-wise, I think that's all I wanted to cover. Now we can start talking about the software. For this particular project, it turned out that the hardware was actually the easiest part. This board worked right off the bat, much to my relief. I didn't have to debug it. It came out perfect on the first try, which almost never happens, but on this one I got lucky. The software, however, turned out to be a lot harder than I expected it to be. So let's go ahead and talk about that. The first thing that I wanted to get working was, once I had the shield ready, I was waiting for the screen. The screen hadn't arrived. So I connected the shield. I followed the instructions on Shabaz's audio notes to try to play some audio, play some feedback, get some feedback that the board was working. I basically copied an MP3 onto it. I played it, and it worked flawlessly. You know, it was just awesome. Everything was good. So I was like, yes, once the screen comes, I'll go ahead and attach it, and everything will work, and I'll be done. So I get the screen, which initially was a BBView 4.3-inch screen. That screen, unfortunately, the software for it is very much out of date. So I was trying to figure out how to get it to work with the latest Debian image, which is what I have on this thing. And that just wasn't working. There's lots of guides, but basically that product hasn't been updated in a while. So if you do have a BBView 4.3-inch screen, you're going to be prepared to do a little bit of work because it's not going to be plug and play. So as I was fighting with that, I spent a good couple of weeks trying to get that to work. I was nearing the point where I was thinking of recompiling the kernel to see if I can get it to work. But in that process, our cleaning lady accidentally threw out that screen. Apparently I had left the box out and they didn't think there was anything important in it, and they threw out the screen. So now I don't have a screen to make on the radio. So here at the office we scrambled and we went and we ordered a 4D Systems 7-inch Beaglebone Cape screen. And that made me glad that the cleaning lady threw out the other screen. This one works plug and play. This one, as soon as you hook it up to the Beaglebone Black, it detects it because it does have the ESProm, and it just plays straight to it. I mean, it works flawlessly. The touch interface is excellent. I was ecstatic. You know, I'm like, yes, it worked. I'm on my way again. So, you know, I was very happy. I start to, you know, get everything ready. I can see the LXDE desktop. On the back of this screen, the other thing that's cool is it actually has space to hook up another cape. So I just plugged in my cape. I hooked everything up. I turned it on. Tried to play the same demo file that I had gotten to work previously. I tried to play that, and it failed miserably. It didn't work at all. And here is where things started to get very difficult for me. Okay. Basically, at this point, I now had to start learning about the device tree overlays. Okay, and there's a lot of links that we're going to kind of talk about a little bit here. So, device tree overlay, what is it? Okay, basically, if any of you have ever seen an overhead projector, maybe in school or at work, you know that on the overhead projector you can put a transparency with text or whatever, and as the light comes through, it reflects onto the overhead, through the overhead optics, and then ends up on a screen. Now, because it's transparent, you can lay several of them on top of each other, and when you lay one transparency over another, you can reveal new information, or you can block old information. Device tree overlays basically work the same way. By default, the Beaglebone Black has its built-in device tree, a few overlays that are set up at startup, and then any item that's connected that requires certain peripherals or anything can request to have another overlay thrown on top. So what happened? When I hook up the screen to the Beaglebone Black, the screen uses the HDMI video output. Okay, so it takes ownership of that. The problem is that when it takes ownership of the video, it also disables the HDMI audio because all of that is together. In my case, my Shield requires that HDMI audio. So when I plug in the screen, I automatically lose the functionality I need to be able to get audio out. And this actually became a very, very long process. I spent, I think, a good 3 weeks dealing with this. So what was the solution? Basically, the LCD screen uses one of the built-in device tree overlays that comes with the distribution. So, you know, that's why it works right out of the box. What I had to do in order to get my Shield to work is I had to make a device tree overlay that basically incorporated the HDMI audio without incorporating any of the HDMI video. And it took a little while to figure out, but in the end, what it basically boils down to is this is the default HDMI overlay that's in the Beaglebone Black. What it boils down to is me copying the audio parts and neglecting the video parts. And the end result of doing that is this file over here, which I'll show you guys. And I actually have a description about how to use it, where it needs to go. So, again, you don't have to worry, it's all here. As you guys can see, And in the George audio cape, I gave it exclusive use of the audio pins set up here. I added fragments. These, again, are parts of the overlay that replace the default one, because, again, we're putting layers on top to enable the pins we want for this shield. So these are all the audio pins. The MCASP module is basically what outputs the I2S signal. And I basically, in the end, I was able to, after a lot of trial and error and a lot of copying and a lot of getting different parts of it, I was able to get this file, which works flawlessly. It gets me the audio. Okay, let me see if there's anything else. That's so far. So that was a mission and a half. But basically, all I really had to do was copy the audio parts out of the default HDMI overlay and put it into my own overlay. Okay, so that was the big, the one that created the most trouble for me, was setting that up. So we got that in. Let's go ahead now, and I'm going to SSH into the Beaglebone Black. I do have it connected. At a certain point, I will show you guys how the interface looks and how it works. But for right now, let's go ahead and just SSH into it. On a Windows machine like I have here, you have to use a program called PuTTY. There are other terminal emulators for Windows, but I find PuTTY works perfect for this. I already have a few settings here. I can double-click it to connect. So I do that. I get my login as. I'm going to go to root. Okay, we'll give it a couple of seconds. It'll log in. Okay, perfect. So first thing, we go to the lib firmware directory. We're going to see these are all of the device tree overlays that come with the Beaglebone Black in this kernel image. A lot of them are made by Adafruit, basically to make sure that out of the box their shields work with the Beaglebone Black. If you look here, you'll find mine. I have the DTS, which is the pre-compiled before, the source file for the device tree overlay, and then the compiled device tree overlay. Okay, very important. This is what is basically running my shield, my cape. So, again, it took a lot of work. Right now, if I do a cat $ slots, this is an environment variable that I set up, I can see all of the shields that are set up and how they're working. So right here, we see the LCD cape, okay, which it always loads up by default, loads up fine. This is the onboard memory. That's always going to work by default. And then these here are the default HDMI overlays. These are what, when nothing is connected, give the Beaglebone Black its HDMI video and HDMI audio capabilities. You can see here there's no L. L means that it's loaded. I've overridden it with my cape. Okay? Now this actually took a long time because when you try to echo into the slots variable, and again I set this up following the instructions on this blog here. Right here, basically he elevated these variables up to an environment variable status, the way they're always accessible. When I would try to put it in, because what you end up having to do to invoke this, to invoke any cape, is you save your compiled overlay here, like I did, and then what you end up doing is you do echo the name of the overlay, let's say that, into the slots variable in this case. Okay. There's a little caveat though. If, for example, it's a very long name or the name has breaks in certain spots, then it won't actually recognize it correctly. And it'll think you're referring to, like in my case, I had these before, and it would just stop at the audio cape part. It wouldn't carry on. So if I typed in George audio cape, this whole thing without the 00A0, it wouldn't recognize it. And the only way I found out was because of the dmessage directive, which is basically following all the kernel commands as they've been running. And you can see where it was having an issue. So that came in handy. That's a good command to be aware of, dmessage. It basically keeps track of everything the kernel is doing. So for debugging, saved my life. I really fought with it for a little while to be able to get that right. So again, we're here. Now, because I chose to not do the ESProm, I had to figure out a way to get the device tree overlay to load up at boot. Otherwise, every time I turned on the radio, I would have to go in SSH and basically apply the overlay. So, a couple of things that you should be aware of if you're doing the same thing. Let's go to the boot directory. Okay. There's a lot of important files here. The most important one is uenvironment.txt. I'm going to go ahead and use Nano to just show it. Now this file, what it does is it basically controls what overlays get brought up at boot. So I went down, anything that has the hashtag or the number sign on it is commented out. I went down and I enabled my cape, and I disabled the default HDMI and HDMI in, since those weren't going to be used anyway. It ends up serving as a cleaner install. So I set this up, I saved it, and I'm like, yes, you know, now next time I boot, it'll automatically start up, and I won't have to do the whole echo into slots thing. So I rebooted it, I went to it, and it didn't work. And that was another battle there, where I wasn't quite sure what was going on. You know, the instructions I had found had said, make sure to, in the uenvironment text file, to include the cape. That way, when you turn it on, it was going to work. So at this point, I went back to the BeagleBoard groups. I looked around, and I found in a frequently asked questions, I found a very specific note about this. And what it was is that the uenvironment text in the latest Debian image doesn't, it runs once, but it doesn't keep trying to get the cape to load up. Because remember, when Linux is booting up, there's a lot of things that are happening, and they're happening in a certain order. And sometimes if the cape doesn't try to load at the right time, it'll fail. But if it would have run later on, it would have worked. So the solution, or the workaround for this for the meantime, is actually to adjust another file. Let me go ahead and show you where that is. So we're going to go to CD, to the etc directory, which is where a lot of configurations are stored, default. And in here, there's a file called Cape Manager. Okay? Cape MGR, this one right here. And this basically is the settings for the Cape Manager software that handles loading capes at boot and actually using capes in general. It checks the ESProm and loads up the appropriate overlay file and all that good stuff. So I'm going to cat that file so we can just see it. And basically what I ended up having to do is, in the case of the screen, of the LCD screen, apparently part of its work, it actually automatically added to this file. It had cape equals the LCD, so that way from default it would always start up. And then I went and I added my audio cape. And that basically makes sure that whenever the radio turns on, the cape, both capes get loaded. Even if it fails once, it'll keep trying until the cape gets loaded. Okay? So that was pivotal. At that point, I had the screen working, and I had my cape working, and I had everything working at boot. So I was pretty pleased at this point. Sorry, guys, I'm drinking some water. It's a little hard for me to talk so much. So got that working, got the device tree overlay working. So now I basically had to determine, okay, I got all the hardware working together now. The device tree overlay is good. Now I need to make the application. I need to make my Wi-Fi radio. And again, there's a million ways to skin a cat. But what I chose to do is to use Python. I'm very familiar with Python. I basically develop in Python and C. For anything embedded or anything microcontroller related, I'll use C. Anything else I can get away with, I'll use Python. Due to the horsepower that the Beaglebone Black has, I could get away with Python, and it was going to make my life easier. So what I ended up doing is on my Linux box, I developed the whole interface. I wrote out the whole thing, and I can show you guys some of the files that were involved. So over here under software, it's a trunk. And this is the main Python code right here. Okay, for my application, I'm familiar with TK interpreter for Python. It's the built-in GUI library. If anyone is a Python developer or is a GUI developer, is probably horrified right now. Most people would say use the Qt library or WX widgets or use something else. But in my case, I'm very familiar with TK-Inter. It's the toolkit of choice for me because I don't do anything that usually has to go out into the world or anything like that. So I decided that I'm going to stick with what I know. And I had always heard it's more powerful than people assume. It can do a lot of stuff. But I actually got to discover that in this project. I really, really encourage you, if you're doing any sort of GUI development, check out TK-Inter. It really is worth your while. This is actually has a very niche application because it's a touch interface. So obviously the buttons are going to need to be bigger than normal. Everything's going to need to be responsive. So I was a little concerned about how TK was going to handle it. And it actually handles it very well. It's very easy to size, all of the buttons, which didn't give me much trouble. There's a lot of good resources available for TK. TK docs predominantly, and then there was one by a university that basically documents all of the functions. So these 148 lines form the basis of the interface. The entire interface is here. Now, obviously there's a lot of room for improvement. There's a lot that we could work with here, but with 150 lines, I'm really happy. So this was the GUI. This handled just the graphical interface part. For actual playing of music, what I ended up using, which a lot of people do for these sorts of things, is I ended up using the music player daemon, which is MPD, and its simplest control interface, which is MPC. Now, MPD, unlike other music players, which you guys may be familiar with, iTunes, VLC, things like that, MPD is unique in that it isolates the mechanism that processes the music, that drives, that actually does the work of getting audio. It isolates that mechanism from the control mechanism, from the interface side. So really, you could couple MPD with any sort of interface. In my case, what I ended up doing is I made a really simple library that would allow Python to call MPC and in that way control MPD. And you'll see this library here. This is MPC. This one's very simple as well. It's only 93 lines. But basically what I'm doing is I'm using a module in Python which can call, the system can call like a terminal, and basically use it to pass on, what station to play, volume settings, what the current song is. To basically, a wrapper is what I did. I created a wrapper around MPC. And that works very well. Very simple, very easy. The final thing I did, and this was, nearing the end of the project, so I was, it's a very quick and dirty hack. What this script does is, this script basically allows me to very quickly add stations to my radio. In order to obtain stations, the best way to do it for me and for this application is to go to a site like Shoutcast. Okay, and Shoutcast basically is a listing of internet radio, of a lot of, I can't say all internet radio stations, but it has a lot. They're organized by genre, by the type of music they play, and basically, if you right-click, you can do a save link as, and you'll save a PLS file, a playlist file. And with that file, what this little script does over here is basically it processes the file and then sends the appropriate command to MPC to add the radio station to MPD. So this is very quick and dirty. There's a lot of things, a lot of checks I could have implemented to make it more robust. But for my purposes, it's just fine. It works fine. You guys can add to it if you want. So that's basically how MPD works. It's the daemon that handles all the work. It's isolated from the interface. Now, what I ended up doing is I had to configure it to work on the Beaglebone Black, and configuring MPD is actually very straightforward. It's not too difficult. There's one main configuration file, and all the magic happens with that file. So if we go here, this is the file. MPD creates it. Basically, what I did was I changed the directories. I didn't want MPD running as root, so I had it run under a user account. And that's all following a tutorial that I linked to in the main page, so you guys don't have to worry about that. The only key point I want to bring up here for you guys is the volume control, okay, and the audio mechanism. So MPD can use pretty much any audio protocol under the sun. It's highly configurable. I mean, for a tool that is actually very simple to use, it's extremely powerful. I don't know why you would use anything other than MPD to play, for this type of application. So I went to audio output, and I set up the ALSA driver, because that's what the inside the Beaglebone Black, that I2S stream, is produced through an ALSA driver, which is Advanced Linux System Audio Linux System Architecture, something like that. And that's what it uses inside the Beaglebone Black. So I set that to be the audio output. I gave it the name. The internal audio output for the Beaglebone Black is called Black, and I set that up. I left the others off. You can use all sorts of streams. You can use an OS. I think you can use PCM. You can a bunch of stuff. So I didn't mess with any of that. The only other thing I did was for the volume, set up the mixer type to be software. If you don't set it as software, then the volume control won't work on the radio. Okay, so if you build this, you have to make sure that this is set to software. Very important. Okay, other than that, everything is pretty much on default settings. So got MPC set up, I got Python set up. Show you guys how the interface works. Let me make sure there isn't anything else I want to cover here. Okay. The icons I grabbed from Elementary, which is a Linux distribution, and you'll see them on the radio. I basically got some icons for the volume, for the play, and for the stop buttons. So that's what's here. This is the entire icon set. I just grabbed a few out of it. They show up here in trunk, which are these right here, these GIFs. These are the various icons. tkinter, by default, will only use GIF. I wrote everything in Python 3, so I don't have access to the PIL, which is the Python imaging library. I could have used something like Pygame or something else, but it was easy enough to convert these to GIFs, so I just did that. This here, this bash script is very simple. It basically just goes to where I saved the interface script to and just calls it. So at this point, I'm pretty much sitting pretty. Everything is working. My application works after I debugged everything. I got audio working. The only thing missing, the only thing missing from getting this to work is to have my Python script run at startup. That was the last thing I had to set up to get this all to work as a cohesive unit. So what I ended up doing, and again, a lot of research, the Beagleboard groups came through for me on that one as well. What I ended up doing is basically the X server, or the desktop software on the Beaglebone Black Debian image is LXDE. So I've found this documentation, which was helpful, but I didn't quite understand it to be able to really leverage it. And then when one of the forum members, specifically, it was, I wrote his name here, Peter Gregory, when he gave me the missing piece. But basically, the way it works is in the LX session area, you go into the config LX session, LXDE, there's an auto start file, okay? And that auto start file basically allows you to specify what you want it to start with, what should load up at the desktop when you first start. So basically, and I'll show you mine, it's a very simple file, nothing too crazy going on here. Okay, basically I commented out these profiles, and what I ended up doing is I ended up setting it up as a kiosk. Basically, the only thing that comes up is my application. You don't see any of the LXD, you don't see the bar at the bottom, you don't see the different, you don't have access to any different programs. None of that shows up automatically. And then I put in the command to start my program, and I also took advantage to start up the Wi-Fi. Okay? So at boot, all of this happens. As soon as it's possible to happen, it'll happen. It'll keep trying until it is successful. That's what the @ symbol in front does. So it's actually a very impressive little setup here, and again, all of that is documented here. It's very, very handy. And that's basically it. Let me go ahead now and show it working for you. Okay? So I'm going to go ahead and stop sharing my screen. I'm going to turn on my camera. Hope this works. Okay, hopefully you guys can still hear me. Right now you're looking at my computer. And then over here, here is the radio. Okay, you can see the little audio. Here's my computer speakers. I use a 3.5mm computer speaker audio output. I'm going to try to get this closer. And then what I'm going to do is I'm going to hit play, and you guys should be able to hear it playing. So okay, the program every 5 seconds basically tries to see if the information for the song that's playing has changed. Okay, so right now I had left this going for a little while, so it'll take a little bit to adapt to update. Great. I got Kesha. Sometimes certain sites will have issues. Hopefully you guys can hear it. Alright, I'm going to change it to something else. Let's put something classical it can't possibly be. Now, something that can happen is if the Wi-Fi starts to have certain issues, in this case I have it straight connected, it does tend to work better if I have it on a wire. The signal works a little bit better. Let me also get out of the volume works fine as well. Lower it, raise it. So go ahead and hit stop on that. Okay. So you guys can see it does work fine. If there's any questions, please feel free to submit them to the chat. That's basically what I wanted to show you guys. And there are a lot of questions. So let me go ahead and move some of this around so I can see it. Okay. Nobody can see. Okay, I can't see anything, some could. But some of you were not able to see what I was showing. Okay. Right now I'm not showing anything. So let me see if I can change that. I'm also going to get out of the putty thing so I can exit that. More putty. I'm going to try to show it again. Can anybody see what I'm showing? Let me know if you can't see it. Okay. Still no video. Okay, Johan can see it now. Can anybody see it? Okay, John can see it. No. Okay, try to click on the panelist buttons or the chat windows. Okay, so some of you are seeing it, some of you are not. But basically here is the interface like I said. If I just hit play, sometimes the Wi-Fi, if it's on its own, doesn't quite work. Like right now I lost Wi-Fi because there's a big ground plane under it. Normally I have it on an external cable, so like right now I've lost it. Yeah, come on, come on. There we go. Yeah, the signal's probably being interfered with because of the ground plane. Okay, but you can see the Wi-Fi is active right now. Everything should be working just fine. Oh yeah, you guys won't be able to hear it because I'm on the phone. But it is working. I would have to like take off my headset and try to put it closer. I'm gonna try that. So hopefully some of you could hear that. It's fuzzing out on me because I had read that you should always use an external cable for the Wi-Fi for the to separate it from the ground plane that's under the USB connector here. But I wanted to try it without it today, of all days, right? Normally I have it connected to a long USB cable, and that works perfectly fine. Okay. So I'm going to go ahead and stop my video. Okay, so that's basically it. Let me go ahead and start answering some questions. Like I said, feel free to send the questions in through the Q&A or through the chat. Some were able to see it, some weren't. The participants windows where you would be able to see it, yes. That's where I had it. Okay. So I know I had a couple of questions here. Let's go ahead and try to answer them. If you'd submitted a question earlier, please send it again through the chat, because now everything's become so heavy. Like there's so much stuff here from people writing that they couldn't see it that I kind of lost it. Just send me the questions again, and I'll be more than happy to answer them. Okay, so here we go. There's a question. How can I edit the property of a group of vias at the same time? I can group move or group copy, but not group property. The way you do that is by using the change command. So what you would do is you would set up, let's say for example you want to change the diameter of all of them. Then you would form a group with the vias. You would go to the change command, select diameter, select what diameter you want it to have, and then you would apply that to the group by either right-click and selecting Change Group, or just holding Control and then right-clicking on the group. That'll work just as well. Okay, hopefully that answers the question, NK. NK has asked me to share my window. Go ahead and do that. So let's go ahead and go back to Eagle. I'm just going to close this, and I'll show you how it works. We go over here. I'll just make a new board. Let's say I have, I don't know, let's say I have these vias here. Okay, so I put all of these vias. And let's say I want to change all of their shapes to round. So I select everything, go here, change, shape, round, and then somewhere within the group, control right click, and they all become round. Same thing if I want to change the drill size, I can go change, drill, pick something really massive, control, right click. Okay, so a lot of the properties can be changed using that command there. Okay? Okay, any other questions, guys? Again, this whole thing has been recorded, so you will be able to see it at the end. Okay. Nothing else has come in through the Q&A. Guys, if there's nothing else, can we place some number of vias in X and Y direction? You mean like, kind of like using like an array, doing a type of an array with a specific distance? You can do an array. So for example, you could do something like this. I'll show you now. So this via is $$1. I have $$6. I have 1, 2, 7. I have 7. So you could do something like tools, element array placement, and you'll put in the prefix. So S $, starting index would be 1, start at 0, 0, and then the spacing in the X would be, I don't know, put 0.5. Five. Let's just say, I'll do a circular, why not? S $, components, there's 7 of them. We're starting at 1. Radius would be, I don't know, 2 inches. Oh, did I type it wrong? S $1. No, that's fine, I did. I was right. $, radius 2, component 7. Oh, you can't do that with the vias on their own. You can do it with pads in the library, but you can't do that with the vias here. I apologize. That was a mistake on my part. But you can do it with components, like with LEDs and stuff like that, as long as it's a component. Vias don't count because they're not considered components in Eagle's parlance. If it were a pad, it would work, but here with the vias, it does. It does not. Okay. So Marnix asked me a question on Eagle 8. If I say anything, I could lose my job. So unfortunately, I can't lift anything there yet. I can tell you that it will probably be a much stronger release than version 7 was. We actually are giving ourselves a year and a half to just focus strictly on Eagle 8 to put in a lot of good stuff. So I can't lift the tip of the curtain, unfortunately. but I'm glad you noticed. That way in the future I can hide it. Unmute us for more. Okay, let me see if I can unmute whoever's on the phone. Let's check. No attendees. Okay, as far as call-in users, I only have 2 people that are calling in. Okay. Can anybody talk? Hello?
Hi, Ora. This is Nader.
Hey, how's everything, Nader?
Good, thanks. Well, thank you so much for the great presentation. I appreciate that.
Very welcome.
The question that I have for you was regarding the ground, the star connection of the ground that you were showing in your board.
Mm-hmm.
And I totally understand, the way that you connect them in one single point to basically make them immune from each other. However, one thing that I just want to know, I don't know if you have also experience with the RF chip, that, the noise is very important to basically to keep the RF portion quite safe from the noisy, especially if you have like a DC-DC converter on the board.
Okay.
What I want to know that, let's say in a board I have an RF chip and also have a DC-DC converter. Usually what I have seen people do, let's say if there is a 4-layer board, they make 2 layers of that ground. Let's say, for example, the top level is more like a signal level, the bottom level is also signal level, and the middle 2 layers are the ground level. Are we supposed to keep those grounds separated and then at one point where it's actually connected to the outside ground, we shore them together, or is it better to put as many vias as we can to make a solid ground between the 2 layers of ground?
That depends on the exact application. In the case of an RF board, what I've seen usually is that's one way to do it, where they'll put basically ground planes in between. That way they isolate what's on the bottom from the top. And then they stitch the living daylights out of it. So they'll put vias like all along the edges, all of that trying to fence and create very, very solid paths to ground to avoid any leakage coming off the board. That's usually what I've seen. It depends on the application. In my application here, what I had going is slightly different because I have an audio DAC board, okay, that's receiving digital signals coming in, and it has to output analog signals. So what you want to avoid there is any noise coming from the digital side, because when you have like in the case of this audio DAC, and I'm going to go ahead and open it again because I didn't discuss very well how it ended up working. In the case here, okay, with the audio DAC board, the I2S stream that's coming in is coming in at 24 or 25.476 megahertz, okay, with sharp edges. At every transition, it's creating noise. It's pumping noise into the circuit. So what we end up doing is, for those parts which are around here, this is the digital section. I just noticed signals coming in over here. Okay, all of the currents, because for any circuit to work, you always have to have a return path. You have to have the ground to come back. Basically, I keep all of those fast transients, I limit them to this polygon. That's the idea of doing the separation. Any fast transients, they're limited to here, and they only return over here. The current always looks for a path of least resistance in the DC case and least impedance in an AC case. So in the general case, least impedance. So over here, there's no motivation for currents that are in this polygon to flow backwards, to flow back over here, because ground is right here, is the central point. Now, the way this actually works that I'm connecting, if I were to run a DRC check right now, you'd see that there's errors here because I'm shorting these polygons together. Okay, all of these polygons have different names. But what I'm taking advantage here is of a characteristic in the way Eagle handles polygons. Basically, polygons are given rank or a priority. This allows polygons, for example, when you have a large ground plane, but somewhere within it you need to have an isolated area or like a heat pad or whatever the application, basically a polygon within a polygon. By changing the ranks, you can cause one to isolate from the other. However, if all of the polygons, as is the case here, have the same rank, Eagle just shorts them together because they all have the same priority. So that's what I did to get all three grounds to connect at this point over here.
I see. And then on the upper part, you have, it's not really narrow, but it's pretty long from the ground plane to the top right corner. Wouldn't be that a little more resistive on the ground side? Isn't it better to have like a wider ground? I don't know how much power that section is consuming, but I'm talking from the L2 all the way to that ground is more like a L shape, inverse L shape.
Yeah. Yeah, this part right here that I'm running over.
That is correct.
Okay. Very good point. In this case, in this usage that I have here, this circuit consumes very little current. So there isn't a lot of drop over here. On top of that, if you look at the thickness of this, which I'm going to try to see if I can turn on with the grid. If we look at the thickness here, every 4 of these is a millimeter. Okay, I'm going to actually put it in mils, because in mils is a very handy rule that I kind of follow. So right now, each of these is about 10 mils, okay? So the thickness here is 10, 20, 30, 40, 50, 60, 70, let's say 80 mils roughly, okay? For every 10 mils, you know, you can safely handle about 500 mils of current. 500 milliamps of current, very safely. The rule holds up until about 4 amps. At that point, the heating becomes an issue, and you know, other stuff gets in the way. But 10 mils.
The rule of thumb is like how much current per mil?
The rule of thumb is for every 10 mils, 500 milliamps of current can be safely passed. Okay, so in this case, I have 80 mils. According to that rule, which is basically, this is the limit here, I could run 4 amps through this, and I wouldn't get an appreciable drop. So because I'm running such little current, it's not too big a deal. And the resistivity of this segment isn't enough to pull the ground potential very high anyway, like to be very different than the rest of them. So for the circuit, it works. You know, I understand if I were doing an RF thing, nah, that would not be okay under any circumstance in an RF situation. But for this situation here, it was more vital for me to keep this circuit here close, and the way these sections ended up working out put that power supply over here. But it was okay because very low power, and this is all this part right here is just power rails. So
sure. And my last question is that, like, whenever I click on the RAD that basically fill the ground for every area that I've selected, I don't know how to undo that unless that I click and delete on that. Is there any command that can undo the RAD?
Yes, there is. Let me go ahead and show you that. This should be a shortcut, and I actually have it as a shortcut, but I'll show you right now. Basically, the command to undo the polygons is rip up, space, @ symbol, semicolon. Hit enter, and they go back.
Got it.
I'll bring it up there again so you can write it down if you need it.
There's rip up, @ semicolon. Got it. Well, thank you so much. I really appreciate all the hints and also the good presentation today.
Thank you. If there's any other question, guys, please feel free to send them in through the chat. I'm still keeping an eye on it. If not, thank you very much for everything today, for taking the time out of your busy schedules to watch this presentation. Like I said, in the future, if you guys have any questions, you can email me, jorge@cadsoftUSA.com or support@cadsoftUSA.com. Okay, so thank you, everyone. Have a great day. I'll put up the link of the recording as soon as it's available.
Thanks. Bye.
Bye, everyone.